Hi everyone. One person coming in now. Hi Ada.
Hi, sir.
Right, I'm going to go through this practice paper. You've got another one coming tomorrow, and this will
Okay.
be sort of. I'd like to try and treat this as a mock and try and submit it. I noticed you didn't submit the one that was due on Monday. It's a bit of a shame. So I'm going to go through it. I'm going to show you how to answer the questions on it. Your
Yeah.
task for this afternoon's lesson is to really sort of go through it yourself. I want you to have a proper look at it and make sure you understand not just what the answers are, but also why they're the answers. So what I'm going to do is I'm going to you have to mute your microphone for a minute. You can unmute yourself if you wish, if you need to ask questions. But aside from that, I'm just going to go through the walkthrough. So do please stop me if you've got a question, but otherwise we'll just make a start straight away as quickly as we possibly can. So what I'm going to do is I'm going to go through. I'm going to go through the through this paper. Now I'm going to switch camera for a minute. Bear with me. There we go. So we're going to do a bit of a walkthrough. So just to talk you through it, remember the golden rules are that you should read the instructions on the front. They're always pretty much the same, but you should make sure you got your programmable, non-programmable scientific calculator. You should make sure that you've answered the multiple choice questions at the very least. They're worth 8 marks in this case, and 75 marks in total on the paper. So there won't be a practical mark, obviously, for this term because we haven't been able to do any practicals. So the next thing to remember is to keep these numbers to hand. So what I would do is I would make sure that I've picked out the numbers that are most useful. Now, most of these numbers are not that useful. The ones that are useful are that one, the Avogadro constant, and the Boltzmann constant. They're the main ones. In terms of your formulae, you've got your sort of your gas laws formulae. That's pretty useful as well. So those are the ones you're going to need from your formula and data sheet. So the first question is really to answer to suggest why people use liquid in glass thermometers in schools instead of digital thermometers. And there are a number of different reasons. We want 2 basic ones. How do we know it's 2? It's because it's 2 marks. So the first one would be that they're cheap to buy. They are very, very cheap to buy. And the other thing is that they do not need batteries. Now you notice that that you need to have a comparison. So here, this is obviously a specific comparison here, the fact that they don't need batteries because digital thermometers do. Cheap to buy. It's worth saying cheaper than a digital thermometer. Okay. So then you've got your thermometry, which you did with Mr. Welsh. So you've got a blacksmith using a thermocouple to monitor the temperature of his fire. The blacksmith is somebody who works by heating up iron and shaping it. The temperature of the characteristics of his thermocouple that he uses to measure the temperature of the fire are shown in figure 1. Just going to try and get a better focus on that if I can. There we are. So you've got a thermocouple, so it's producing a voltage or an EMF, and as the temperature increases, you can see that the EMF produced increases until you get to a transition point, and then it goes back down again. So you have to, so maybe that's going to come into play a little bit later. So the next part of the question says, use the data from figure 1 to estimate the EMF of the thermocouple at 400 degrees Celsius. Give your answer appropriate number of significant figures. So if we draw a line vertically up from 400 and then vertically and then horizontally across, you've got a certain distance. Now, the way to do this, to do this most accurately, is to use your ruler. So here we've got, if I line this up perfectly, it's 24 millimeters, okay? So 24 millimeters equals a difference of 10 millivolts. So here we've got 18. So it's 18 millimeters implies, well, you need your calculator for the next bit. I'll find my calculator. I've got it's under a pile of papers. Here we are. So if I've got 24 divided by 10, that means every 2.4 millimeters corresponds to 1 degree. Sorry, corresponds to corresponds to 1 millivolt. So if I multiply it by the 18 millimeters, I get 43.2. Is that right? Let's just try that again. So 10 divided by 24, so 4.16, sorry, 2. Okay, multiply it by 18, gives me 7.5. So that would be 7.5 above 10. So that would be 17.5 millivolts. Now that's not an appropriate number of significant figures. So really, I would say 18. That's my final answer. Whenever you've got a final answer, you double underline it so that's clear that that's your answer. Next question. It says, describe the difficulties in calibrating thermocouple with temperatures around 600 degrees Celsius. So at 600 degrees Celsius, you can see that there's actually either side of 600 degrees Celsius, there's very little change in the EMF. So there's very little change in EMF for temperatures either side.
Sorry, sir, I can see the question B.
There you go.
Thank you.
Okay, there you go. Thank you. Either side, just a paper slipped, either side of 600 degrees Celsius. So the idea is I'm being very, very clear. I'm being very, very clear. It's only one mark, but I've got to be clear. It's not enough to just say it's inaccurate. So the middle of a volcano is very hot and dangerous. Suggest and explain what type of thermometer would be used in measuring the temperature of the surface of the sun. Well, it should be surface. It should be the middle of a volcano. It's just a typo. So the idea is meant to be that you would suggest a pyrometer. And that's worth 1 mark, but it says suggest and explain. So it's pyrometer, and in both cases, whether it's surface of the sun or the middle of a volcano, no need for a direct measurement. Okay, and that would be worth you 2 marks. 1 mark for suggesting, 1 mark for explaining. So then we're on to the graph question, and I know people don't like the graph question, but for your UFP exams, if you're not actually in Brook House, you are going to need to make sure you've got your graph paper, or you've printed out the exam paper when it arrives and done it that day. So you need to really do that. So it says a student investigates behaviour of a gas cylinder in isochoric change. So it isn't. It's isobaric, but never mind. It says state Charles' law. So Charles' law is basically 2 things. You've got to put the caveat in first. So it's for a fixed amount of an ideal gas. Remember, it has to be an ideal gas. Well, Charles' law is constant pressure. Constant pressure. The volume is proportional to absolute temperature. Okay, now what's important to get 2 marks? So first of all, the first bit is to get the fixed amount, ideal gas, constant pressure. That's worth 1 mark. And then you say volume is proportional to, it has to be absolute temperature to get the 2nd mark. It then says state two quantities which assume we have to keep the same. Well, this is pretty simple. This is actually linked to the first question. It's the amount of gas and the pressure. Now, you can get away with saying mass of the gas, but really you should say amount of gas. Okay, so amount of gas and of course the pressure of the gas. Sufficient to say pressure. So the next part, you are just filling in a table. So when you're filling in the table, it's got temperature in degrees Celsius and you want absolute temperature. So the first thing says calculate the values of T in the table. Oops, I've gone off the bottom. Calculate the values of T in the table using correct number of significant figures and suggest a suitable unit. So the unit would be in Kelvin if it's absolute temperature. And I have to add 273 to each of those values. So if I add 273 to each of those values, you get 629, 534, 440, 346, 314, sorry, I've missed one, 408. Then it's 346, 314, and 283. Okay, it's just very, very simple. And as everything there is to 2 or 3 significant figures, 3 significant figures is sufficient number of significant figures. You could add 273.14, but really that would be going into 5 significant figures, which is not necessary and not appropriate. So then it asks you to plot a graph of volume on the y-axis versus absolute temperature on the x-axis on the graph they provided and draw a line of best fit. So again, we've got to follow the basic ideas here. We've got to follow the basics of graph drawing, and it's a skill that's a necessary skill. So if we're thinking about it in our values, we know that our volume, which goes on the y-axis, it goes from 0.09 up to 0.009 up to 0.02. So you want to use as much of the graph paper as you possibly can. So I'm just going to move the camera out a little bit so we can see a little bit better. Bear with me for a few seconds while I do that. There we are. Refocus there. So I'm not going to start at 0 here. It wouldn't make any sense, but I would start at 0.008 and go up in twos. So 0.010, 0.012, 0.014, 0.016, 0.018, 0.020, and that's the highest it goes. So our values, our graph, is going to have the lowest value up down here and the highest value up here, and there's not much room up off the top end of the graph beyond that. So that's an appropriate scale. So we draw our axes on as carefully as we can with a ruler, arrow on the end, and we label it. Well, that's going to be volume. Now, what do they use in the question? They use meters cubed. So that's in meters cubed. Now, for the x value, we're going to go from temperatures from 283 up to 629. So I don't think, if I try to start at 250, I could say 250, 300, 350, 400, 450, 500, 550, goes off the end of the graph for 600, so it wouldn't fit, so I've got to halve it. So I'd start off at 200, and maybe each big square would be 100. It's not perfect, but it's sufficient. And I don't go above 700. So that then gives me my graph, my x-axis. And again, I label it. So we label the x-axis. This is going to be absolute temperature, and it's in Kelvin. It's in degrees Kelvin. You can put a little degree sign there if you want to, but it doesn't matter. So then if we're plotting our numbers, So we're starting off at 0.09 and 283. So 0.09 is halfway between the two here. That's 0.09 there. And that would be 283. So that's 283, about there, I reckon. So the next one is 0.10 and 314. So that's 310. 314 is about halfway. 0.11, which is here, and that comes out, that's 346. So that's 300, 10, 20, 30, 40, that's 50, so 46 be about halfway. Notice I'm using crosses, not dots. For 0.013, we've got 408, so that's 400, well 410 is there, so 408 is just going to be just before it. Next one would be 0.14, which would be 440. So there's 400, 10, 20, 30, 40. Next one would be 17, so up here somewhere, and 0.017, which would be 554. So there's 500, 10, 20, 30, 40, 50. That's 60. So halfway between the two, roughly, would do nicely. As long as you're within about half a small square, you're okay. And 0.020, which is up here, would then be 629. So 600 is here. So 629, 610, 20, well that's 30. 29 is just a fraction below it. So it'd be about there. So this should all fall on a nice straight line. I'm just going to double check this number here. 534, that doesn't look right. 10, 20, 30, 4 is there, so that's more like it. And then draw a nice straight line, line of best fit. It's a single straight line. You know you're always measuring gradient from these, and all you've got to do really is then extrapolate it, make it a bit longer, and that's your graph drawn. Okay, that's that bit done. So the next part to do, it then says, explain whether or not this proves Charles' law. So you've got to say whether or not it's proving Charles' law and explain how it proves it. So it's not enough to say a straight line through the origin because the origin's not on the graph, okay? So Charles' law, remember, is that the volume is proportional to absolute temperature. So we know the volume divided by the temperature for any readings should be a constant. Okay, that's part of Charles' law. So I'm going to take 3 readings of volume and temperature. I'm going to take one at about here. I'm going to take one in the middle. And one at the top end, I think. So if I take my corresponding readings, you've then just got to read them. So that's 270. That's 1, 2, 3, 4, 5, 6, 7, 270, and that's 0.8. That's 0.8246, 0.086. This one is 500, and that's 0.0. Let's see, 14. That's 152468058. 0158, sorry. The next one was at 700, and I would make that 0.222222. And all I then do is I take my values and I divide them. So we know that if I take my 3 values that I've measured, 0.0086, divided by the corresponding value of 270 for the temperature. And I do exactly the same for 500 and 0.158. And exactly the same at 700. Oops, 0.0158. Okay. If I divide one by the other, what I end up with is three numbers. So get 3.19 times 10 to the minus 5, 3.16 times 10 to the minus 5, and 3.17 times 10 to the minus 5. Well, they're roughly the same. So they're similar, and therefore Charles' law is proven, because those three are pretty much the same. They're pretty much constant. Okay? Okay? So that's how you go about proving it. Now, the next part is on the graph. It asks you to measure the gradient of the line. You know that's always coming up in these questions. You measure the gradient of the line, give the answer with appropriate units. So no point reinventing the wheel. I've got some measured values, so I might as well make good use of those. So if I draw my triangle here, got a nice big triangle, okay, that gives me greater level of precision. And all I'm doing then is I'm doing exactly the same as I always do. Y1 minus Y2 over X1 minus X2. So Y1 is 222 and 86. So divided by X1 minus X2. So we start at 700, go down to 270. Put the values on, it shows that you've read it correctly. What was it? 270, reminding myself. Okay. Then you just calculate it. So you get your calculator out, you calculate it, and it comes out to be 3.16 times 10 to the minus 5. There's your first answer. So you scored 2 out of the 3 there. You get 1 for using it for showing a big triangle, 1 for correctly showing the correct method for using your for measuring your gradient. The last one is appropriate units. So for that, you need your graph. So it's the units of y divided by the units of x. So the units of y is meters cubed, it's a volume, and divided by that, well, it's Kelvin, so that's going to be Kelvin to the minus 1. And that's your appropriate unit. Then says you've given a formula. It says the equation linking volume and pressure of a gas is given by a particular formula. There it is, and it should be familiar to you by now. You've got to use your answer to this question to calculate the number of moles of the gas. So what you're doing is you're using the formula and you're comparing it with y equals mx plus c. Now the plus c bit is obviously irrelevant because that would just be 0, because that would be plus 0. So this bit here is your gradient. So you'd use your answer. So you'd say the gradient is equal to, well, the gradient is going to be equal to the number of moles times the universal molar gas constant divided by pressure. Okay, so that's exactly the same as what's in that box there, because T is on the x-axis, V is on the y-axis, so it should be the gradient of the graph. So I want to work out n, so rearrange it, we make n equals the gradient multiplied by the pressure and divided by the molar gas constant. Now in this particular case, the pressure is very, very low. It's about 10 to the power 3 pascals, so it's about 1/100th of an atmosphere, but never mind. So we're using this formula, so n is therefore going to give us the number of moles, which would be the gradient, which is calculated from here, 3.16, multiplied by the pressure, which is 1.0 times 10 to the power 3, divided by the molar gas constant, which is on your formula sheet. Molar gas constant is 8.31. And we end up with a very small number, 0.0038 moles. Okay, that's it. Easy as that. It then says predict what temperature would be measured for a volume of 0.045 meters cubed in this experiment. So if you've got that volume there, you know that your gradient is 3.16. So we know that the volume would be the gradient, this bit here, which is your gradient, multiplied by the absolute temperature. So the absolute temperature is going to be the volume, which is 0.045, divided by 3.16 times 10 to the minus 5, which then comes out to be about 1.421. Okay, well, two significant figures will do here. Okay, and that's your temperature. So all I've done there is I've taken this formula here. I know that that factor there is my gradient, which I've measured up here. So I know the volume is the gradient times the absolute temperature. So volume is the gradient times the absolute temperature. I've then just rearranged it to make temperature the subject. So that's the volume divided by the gradient, gives you the absolute temperature. And then I've then just done the calculation. It's pretty easy when you actually know what to do. So the next question is a molecular kinetic theory question. So you know you always get a thermometry question, then you get a macroscopic gas laws question, ideal gas questions, and then you get something that's molecular kinetic theory, but usually sort of mixed in with normal ideal gas laws. So you've got a balloon, it's filled with carbon dioxide. You're given the volume. How do you know it's the volume? Well, the unit's in meters cubed, so that's got to be the volume. Okay. And you know the absolute temperature. It tells you it's 200 Kelvin. Don't have to do anything to it. We know it's 100 kilopascals. That's 100,000, which is 10 to the power of 5 pascals is the pressure. So then it says show there are approximately 4 moles of carbon dioxide in the balloon. So we use PV equals nRT. We say that N is equal to PV over RT. So the pressure is 10 to the power of 5, multiplied by the volume, which is 0.1, divided by R, the molar gas constant, which is 8.31. It's on the formula sheet, multiplied by the absolute temperature, which is 300. So that then gives you a number which comes out to be 4.01 moles, which is approximately 4 moles. Okay, so the mark is really for using that formula for correct substitution. You don't get a mark for the final answer because you're proving what the final answer is. Now, in the subsequent questions, as this is structured, you can use 4 or you can use 4.01. It's up to you, as long as you show correct working. So, calculate the mass of carbon dioxide in the balloon. Well, if that's 400 grams per mole, 44 grams per mole, you've got 4.01 moles. It's 44 times 4.01, which comes out to be 176 grams, which I'm going to put that into kilograms because I've got a sneaky suspicion I'm going to need that later on. Okay, you can leave the answer in grams if you wish, or you can convert to kilograms at this stage. It's only 1 mark anyway. So calculate the number of carbon dioxide molecules. So we know that we've got 4.01 moles, and to work out the number of particles in a mole, we use the Avogadro constant. The Avogadro constant is the number of particles in a mole. Well, it's actually the number of atoms of carbon-12 in 12 grams of carbon-12. And that's 6.02 times 10 to the power 23. And that comes out to be 2.41 times 10 to the power of 24 particles. There's no units, just a number. The next step is to calculate the average kinetic energy of one molecule. So to do that, use the Boltzmann equation. We know that kinetic energy of one molecule, of one particle, is 3/2 kT. Now that actually tells you that formula here, okay? So the next one is to then just do the calculation. So 3/2 is 1.5 multiplied by 1.38 times 10 to the power minus 23, because that's the Boltzmann constant. That's there, 1.38 times 10 to the minus 23 joules per Kelvin. Multiplied by the absolute temperature, it's 300 Kelvin there, so 300. And we end up with 6.21 times 10 to the minus 21 joules, okay? It then says, hence calculate the total internal energy of the helium in the balloon. So if that's the kinetic energy of one molecule, then to get the total, we need the number of particles multiplied by the kinetic energy, which, okay, well, the number of particles we said before was calculated in the previous part of the question. So you calculated it here, 2.41 times 10 to the power 24. So that's 2.41 times 10 to the power 24 particles, multiplied by a previous answer up here, 6.21 times 10 to the minus 21 joules. Tells you that you should end up with an energy of somewhere around about 1.50 times 10 to the power of 4 joules. Okay, quite a lot of energy there. It then says the balloon is placed in the freezer and its temperature becomes minus 13 at the same pressure. What is the new volume of the balloon? There are a couple of ways of doing it. You can use PV is equal to nRT because you know the pressure, you know the you want to know the volume, you know the number of moles, you know the universal molar gas constant, and you know the absolute temperature. But it's probably an easier way to do this. So first of all, we've got to convert that into kelvins. So we have to add 273 to minus 13, which makes you 260 Kelvin. Now, the way you can do this is we know that the temperature divided by the volume is equal to a constant. Okay. And so we know that T1 over V1 equals T2 over V2. I want to know what V2 is. So V2 is equal to T2 times V1 over T1. So T2 is 260 multiplied by the original volume in the question, which is given to be 0.1. Divide it by the absolute temperature we started out with, which again, we go to the beginning of the question. It tells you it's 300 Kelvin. So it should give you a volume of less than 0.1. So that you just plug that into your calculator and it comes out to be 0.067. Well, it's 6 reoccurring meters cubed. Okay, it's worth 2 marks. 1 mark for the use of the correct unit. So you can use PV is equal to nRT if you want to, or you can use the ratio trick if you want to, and the second mark is for the answer. It then says, what is the root mean square speed of the carbon dioxide molecules at this new temperature? So you've got to be very careful. We know that PV is 1/3 times the number of molecules times the mass of each molecule times the mean square speed. So we want to work out the mean square speed. Well, first of all, we know that if you've got several molecules, each of a given mass, the number of molecules times the mass of each molecule gives you the total mass. Okay, so I'm going to call that capital M. So I could then say that's equal to 1/3 times the total mass of the carbon dioxide, because we know that, times the mean square speed. So if we know that, then we just want to work out the mean square speed. So mean square speed, first of all, is equal to, well, it's pressure times volume, divided by a third is the same thing as multiplying by 3, and divided by the total mass of the gas. There we are. We want the root mean square speed, so I need to square root it afterwards. So it's the square root of 3 times by the pressure, which is 10 to the power of 5, okay? Because it tells you here it's 100 kilopascals, times by the volume, which is 0.067, divided by total mass. Well, we haven't changed the amount of gas, so it's still 0.176 kilograms. Okay, so that's your mass there. That's your total mass. So if that's the case, then we just plug it into your calculator and you end up with 338 meters per second. You can round that off to 2 significant figures, but 3 is fine. Okay, so that's how you do that bit. The next one then says the student dips the balloon in liquid nitrogen at minus 200 degrees Celsius. Suggest what happens to the balloon. So here we've got to suggest. Now, suggest means you don't have to know the answer, but you have to think about it. We know the balloon will shrink. And for a 1-mark question, that's enough. But if it was a 2-mark question, you might have to think beyond that. Well, if it's carbon dioxide and it's minus 200 degrees Celsius, well, carbon dioxide may change state. So no longer behaving like an ideal gas, okay? In fact, carbon dioxide at minus 200 degrees Celsius, that's at atmospheric pressure, is actually a solid. So then it says, possible to derive this formula. You do have to know how to derive that formula. It is in the notes I've given you, and it's also on the Seneca Learn activity that I've given you. You do need to know the derivation of this formula, so yeah, it's another thing you do have to study. It then says list the 5 assumptions. Now there are lots of different assumptions. The main 5, the key 5 that you need to know is, first of all, we assume that there are many particles, a large number of particles, okay? We assume random motion, all moving in random directions. Okay, we assume they're all moving at random, in random directions. What's random motion? Just random motion will do. We can also assume the particles, the volume of the particles, or the molecules or atoms, are very small compared with the distance apart. Okay, otherwise it wouldn't be compressible. We assume that there are no forces between the particles. They don't attract or repel each other. You could say no intermolecular forces if you want to. And we assume that all collisions are elastic. In other words, no kinetic energy is lost. Well, that makes sense, because otherwise the gas would just cool down to absolute zero just by sitting in a vessel, which doesn't happen. Okay, that's it. It's five assumptions for 5 very easy marks if you memorize them. Right, so now to specific heat capacity. This is something you did with Mr. Welsh. You've got a water heater, heat rated at 1,000 watts. You've got 5 kilograms of water poured into the water heater at 20 degrees Celsius. And it takes 30 minutes to reach a boiling point of 100 degrees Celsius and 100 minutes for half of the water. So that's 2.5 kilograms to boil away, to change state into a gas, in other words. So then it says calculate the specific heat capacity of the water. So now the energy is the mass times specific heat capacity multiplied by the change in temperature. Now it's being supplied by a heater with a given power, 1,000 watts. So that's going to be power times time in seconds. So we need to do a couple of quick calculations. First of all, the change in temperature starts at 20 and goes up to 100. So that's 80 Kelvin. And we know that the time is 30 minutes. So that's 30, and there are 60 seconds in a minute. So it's 30 times 60, okay? So that's 1,800. So as you then do your calculation, then got to work out what specific capacity is. So C is equal to that power times the time divided by the mass and the change in temperature. So the power is 1,000, so substitute times by 30 times 60 divided by mass, which is 5 kilograms, times by change in temperature of 80 Kelvin, and it comes out to be 4,500 joules per kilogram per Kelvin. There's your answer, okay? So you get one mark for correctly calculating the time and the change in temperature. You get 1 mark for using that formula, particularly that substitution there, and you get your 3rd mark for the actual answer. Then it says calculate specific latent heat of vaporization of the water. So we know the energy you put into changing state is times the mass that changes state multiplied by the latent heat. So if we want to work out the latent heat, we know that that's going to be energy you put in divided by the mass. So the energy, remember, is power times time. So the power, remember, is still 1,000 watts, multiplied by time. Now it tells you it's 100 minutes. So that's 100 times 60 divided by the mass, and it tells you half of the water is boiled away. So you started out with 5 kilograms, 2.5 kilograms must have changed state into a vapor or a gas. So it's over 2.5, and you end up with 1.2 times 10 to the power of 6 joules per kilogram. There's your answer, okay? Now, discuss, it then says discuss. Discuss means state it and give a reason, okay? Discuss giving reasons whether the values you calculate like to be higher or lower than the actual values. So the calculated values are going to be higher. The reason being is that there's some heat lost to the surroundings. If there's heat lost to the surroundings, then you need more energy needed to raise the temperature or change state. Okay, simple as that. Then it says describe one improvement to the experiment to obtain a more accurate value of specific latent heat of vaporization and specific heat capacity of the water. Justify your improvement. So one improvement you could do, well, I would insulate the kettle, insulate the water heater. And this is to reduce heat losses to the surroundings. Okay, that's it. That's the job done. 1 mark for describing one improvement, and then 1 mark for the justification for the actual reasoning. Okay, relatively simple. Okay, this was in the this was when I was helping you to revise changes of state and latent heat. I did point out that you do need that in order to measure the specific heat capacity or to measure the specific latent heat, you could insulate whatever it is you're trying to heat up to prevent heat losses to the surroundings. So the energy going into heating up the substance is just heating up the substance, not heating up the surroundings. Right, then you get a nice question on thermal expansion. Okay, you will always get a question on thermal expansion, and we talked a little bit about some of the applications of it. And in this case, we've got a meteor entering the atmosphere from space. It's made from iron. It's made of iron, and the data on it is shown. So you've got the size, the diameter, material, and the linear thermal expansion coefficient. So once you've worked through that, you can then say, well, okay, you calculate the expansion of the diameter of the meteor at 1600 degrees Celsius. So we know that the expansion is simply the original length at 0 degrees Celsius multiplied by the linear thermal coefficient multiplied by the change in temperature. So that's 200 multiplied by 1.2 times 10 to the power of minus 5 multiplied by 1,600. So if that's the case, you then end up with something in the region of, excuse me, my notes, of something in the region of 3.84 meters, okay? And that's your expansion. Now it says calculate the overall diameter of the meteor at 1,600 degrees Celsius. The overall diameter is going to be your 200 plus 3.84 meters. So that would be 203.84 meters. But of course that is irrelevant because the measurement here is implying it's only to the nearest meter. So really I should say 204 meters, okay? Now the meteor lands in the ocean. Suggest what might happen to the meteor as a result of sudden cooling. Well, first of all, start with the obvious. It'll reduce in size, okay? It'll contract, okay? Now it may, if it's cooled suddenly, it may fracture, okay? Or break up. The reason being is if you've got a meteor and it's hot, if you take thermal energy rapidly, it'll take it first of all from the outside. So the middle bit will still be hot, and because the middle is still hot, this bit will be trying to stay expanded. This bit will be trying to contract. So what will happen is that it'll basically crack. That's why if you're washing glasses, if you're washing something made of glass in very hot water, and then you pour cold ice water into the glass straight away, it tends to break. So on to the next one. It then says table 3 shows the data for different materials. So you do remember one of the key skills of UFP physics is being able to work with data. So here we've got times 10 to the minus 6. So we've got the thermal the expansion coefficient of iron is 1.2 times 10 to the minus 5. So for iron, it would be round about 12 times 10 to the minus 6. Okay? Because that is 1.2 times 10 to the minus 5. It's the same number. So it says, place a cross through materials which would expand more than iron at high temperatures. So we're looking for values which are higher than 12. And that's all you're doing. It's very, very easy. Job done. It's as easy as that. All those values are higher than 12. So we're just left with chrome, glass, lead, or not lead, platinum, and titanium, okay? Suggest a situation where thermal expansion is useful. Well, one of the ways we'd do that is it would be useful in thermometers. You don't have to describe it in any great detail. Thermometers or thermostats. The thermostats in some older gas ovens use a strip of 2 metals, that when it's heated, the outside expands more than the inside, so it causes the whole thing to bend like that. So you can, and then it operates a little valve which shuts off the gas when the oven gets nice and warm. So that's one particular way you could actually use it. There are lots of other uses. You can also use thermal expansion to remove remove bolts and lids that are stuck. Okay, because if you've got a nut and bolt, like that, if you heat up the nut, what happens is the nut then wants to expand, and as the outside expands, it then pulls away from the actual bolt, so it loosens it. Okay. And where it's not useful, well, there are lots of different descriptions of where it's not useful. You could use it for things like building bridges, railways. So if you're building a railway, for example, what you'd have is you'd have to have a gap in between your two sections of rail, because otherwise what would happen is that when the rail gets heated up by the sun, these rails expand, and if they're already touching each other, they'll push against each other, and it could bend the railway line. So that's that one. Nice and easy so far. It then says you've got to use first law of thermodynamics. You'll always get something directly related to first law of thermodynamics. While the air in tires can become hot, so we're using the first law of thermodynamics. So we know that tires contain compressed air. So compressed air has had work done on it. Okay. Now it's two markers. And it says use the first law of thermodynamics. It says use the first law of thermodynamics to explain it. So if we think about it, the work done is P times delta V. So what you've done is you've compressed it. You've done work on the gas. You know that the internal energy of the change in internal energy of the actual gas is equal to the thermal energy supplied. Well, we've not supplied any thermal energy, plus W. So that is equal the work done, sorry, the thermal energy supplied to the tyres when you don't deliberately heat them, so that's 0. And the work done on the tyre is positive, okay? Because the work done is positive, then the internal energy of the gas in the tyre is going to go up, okay? Particularly when you've just inflated the tyre. And opening the door to a refrigerator overnight will not cool the room down. Well, if we think about it, what we're trying to do is we're saying that the change that the thermal energy we're supplying is negative, but then you have to do work on the gas. Okay, so what we end up with is the idea that we end up with the idea that that the energy removed from energy removed from the air is going to be equal to thermal energy transferred minus W, because it's being removed. Okay, so it's minus W. Okay, so the whole idea is that if you think about it, another way to look at it is to look at it graphically. We want to have the cold air in the room. We know that we have the hot sort of back of the radiator. We've got the pump, and we're trying to pump thermal energy from cold to hot. okay? The way we do that is we put work in, okay? So you've got more energy heating up the hot part of the refrigerator, okay? So that way we know that if you just leave your refrigerator door open, it won't cool the room down. If anything, it'll heat it up slightly, and that's your answer. So the bit that a lot of people missed when I was doing the when I was going through marking, a lot of people missed out the multiple choice questions. They're very, very easy. You just got to read them carefully. So the first part is looking at the answers, is looking at the question, sorry. So you draw a circle around the letter next to the correct answer. Each question is only one correct answer. The temperature of a body is 100 Kelvin, is increased by delta theta as measured on the Kelvin scale. How is this temperature expressed on the Celsius scale? So what we've got to do is...
Sir, what is different between B and C?
B and C, here that's plus, that's minus.
Oh, okay.
Now, you've got to be careful here.
Okay.
Because it's 100 Kelvin. So it's, to get it on the Celsius scale, it's 100 plus that change in temperature minus 273. So actually, because it was there was a misprint on the paper, it's actually none of them. So we're going to ignore that one. The temperature of water enters a boiler at 12 degrees Celsius. The rate of flow of water through the boiler is 0.05 kilograms per second. The output temperature is 52 degrees Celsius. You have to calculate the power. So the power times the time is the mass times specific heat capacity times the change in temperature. If that's the case, well, we know the power is the mass over time. Well, that is that value there, okay? So it tells you that's 0.05 multiplied by, it tells you it's 4,200 joules per kilogram per Kelvin, multiplied by the change in temperature. So go from 12 to 52, that would be 40 Kelvin. And that comes out to be, bear with, that comes out to be 8,400. So somebody who's not paying attention would select A, but A is not the correct answer because that's kilowatts, and this is 8,400 watts. So the one that's actually correct is C and not A, okay, because it's 8.4 kilowatts. So as we move on, you've then got a graph which shows the temperature change delta theta for the time of 1 kilogram of the substance, initially solid at room temperature, is heated at a uniform rate of 2,000 joules per minute. So we know that that's going to be solid there, liquid, and melting there, okay? So it melts from a solid to a liquid over this particular period of 3 minutes. So what does it say? It says after 4 minutes of heating, all of the substance is liquid. Well, no, because after 4 minutes, it's just got to melting point, but it's not melted yet, so that's not correct. After 10 minutes of heating, all the substance is gaseous. So 10 minutes, well, we've not had a change of state up here, so that's not true. The specific heat capacity of the substance is greater when the liquid than when solid. Well, if we think about it, the specific heat capacity would be how difficult it is to heat it up. And here, it's heating up. It's heating up much more slowly when it's solid than it is when it's a liquid, which implies that the heat capacity when it's a solid is actually greatest because the energy has been supplied at a constant rate. So that's not true. So it must be D. And you can actually calculate it. I know it involves a calculation. You're told the specific latent heat of fusion is 600 joules per kilogram. So if we think about it, if it's for 3 minutes, and it's 2,000 joules per minute, it's a certain amount of energy. Okay. and you're told it's 1 kilogram. There's your mass. There's your energy, but it's the energy for 3 minutes. So that's 3 times 2,000, is your energy that's supplied, is equal to 1 times specific latent heat of fusion. So that's 6,000. So that one is your correct answer there. You've then got to work out the approximate number of atoms in 1 cubic meter of an ideal gas at a temperature of 300 Kelvin, a pressure of 10 to the power 5 pascals. So here we're given a number, but it's kind of disguised. That means the volume is 1 cubic meter. Okay, so we know the volume, we know the pressure, we know the absolute temperature. We don't even have to convert it to Kelvin. It's already done for us. So we're using PV equals nRT. So we want to work out what N is. So N is PV over RT. But then you have to multiply both sides by Avogadro's number to get the number of atoms. Okay. Okay. So then we just plug in our numbers. Well, pressure is 10 to the power of 5. It's 1.0 times 10 to the power of 5. Volume is 1. Na is 6.02 times 10 to the power of 23. Whoops. 23. Divided by molar gas constant. Divided by the absolute temperature. And we end up with something in the region. Bear with me. Something in the region of about 2.5 times 10 to the power of 25 particles. Okay, that's pretty easy so far. Last page of questions, I think. It's got the temperature of fixed volume of an ideal gas is raised from 300 Kelvin to 330 Kelvin. So the mean energy of the particles of the gas increases by 10%. Well, if the temperature increases by 10%, then the internal energy of the gas will increase by 10%. So the mean energy of the kinetic energy of the particles, that's correct. The mean square velocity of the particles or speed of the particles of the gas increases by 10%. Well, you know that's going to be proportional to the kinetic energy. So if the kinetic energy is increasing by 10%, so too must the mean square velocity. So that one's correct. Number of kilojoules per second with the walls of the container increases by 10%. Not necessarily. Not necessarily. So I'm going to say no to that one. So the answer is that only 1 and 2 are correct. Okay. So 5 molecules are moving with speeds and directions shown. Well, it doesn't matter about the directions. It's not shown. The directions aren't on there. You've got 5 particles, and it says what's the root mean square speed of the particles. So you've got to be careful. So you've basically got to add 300 squared plus 100 squared plus 300 squared plus 300 squared plus 500 squared. And that gives you the total squared speeds, which is 53,000. As you've got 1, 2, 3, 4, 5 particles, you divide it by 5, gives you 10,600. You then square root the answer, and you end up with 325 meters per second. Okay. So remember, if it's the root mean square speed, you've got to square the speeds first, calculate the mean, and then square it because it's the root mean square speed. Sometimes you get asked just for the mean square speed when you don't have to square root it, but this question is asking for it, so you have to square root it. Very common mistake in exams. Number 13, what happens to the temperature of a gas as it escapes from a high pressure cylinder? Well, the temperature, if we think about it, it expands. And as the gas expands, that implies it does work on the atmosphere. So it does work is done by the gas. If that's the case, first law of thermodynamics would imply that its internal energy would decrease. So it decreases, okay? Number 14, which of the following does not change during an isobaric change? Isobaric, bar is pressure. So it would be iso means the same. So same pressure. So the thing that does not change is the pressure. Okay? Right, are you okay with that?
Yes, sir.
Any questions about any of that?
I will ask just one question
Sure.
about all lesson.
Yeah.
Can I find this lesson on the YouTube, your YouTube channel?
Yeah, the lessons are all on my YouTube channel. Bear with me, I'm just going to go back to my video of me. My lessons are on the YouTube channel. They're also directly linked. If you go back to the lesson on Show My Homework, you should be able to then access the lesson and actually watch it all the way through. So if you go back over the Show My Homework tasks, where I've put on a live Zoom lesson, you will see that there's actually a recording of it. In fact, this lesson itself is also being recorded. So you'll be able to actually observe the lesson and listen to what I'm saying. Obviously, that's passive, so I wouldn't try and just use passive methods to try to learn the physics. There should be the active work as well. I've set you quite a bit by Seneca, which I would recommend very, very strongly. It's a very, very good way to sort of recap what I've said. And also there's of course a lot of tasks that you can have a go at. Okay.
Yeah, because I think it was so important lesson, and we could repeat maybe 2 times or 3 times.
Yeah. So I would go on the YouTube channel. If you go to my if you click on the link, because in about half an hour's time you'll see that this is up on the lesson as a recording. If you go to watch the recording, you'll see that on all my other videos on there on the YouTube channel, I've tried to sort of label them as clearly as I possibly can for you. Obviously, ignore the A-level walkthrough papers because you're not doing A-level. But if obviously there's lots of UFP walkthroughs and lots of explanations and things. So do please make good use of that, and do please make good use of your of the videos on the channel. But it's the active learning stuff. It's the working through the Seneca tasks that are on Show My Homework, for example. Very, very important, because if you're working through the Seneca tasks, then you're actually thinking about the physics, and when you're thinking about the physics, it's much easier to remember it. So do take on board that advice. Now, when you are doing the exam week after next, there's a mock exam which I've given you for Wednesday to do. I'd like to treat it like the real exam. So if you're at home by now, you should have the wherewithal to print out. If not, you should have some graph paper. I'm going to insist that you have a go at the whole paper, including the graphs, and that goes for anybody else who's watching this recording.
I will print the graph paper.
Yeah. So treat this as a practice for the real thing, not just in terms of just answering the physics questions, which obviously is very important, but also look at it in terms of practicing for taking the UFP exam. Does that make sense?
So yes, sir, it makes sense. How long we have for exam?
The exam is an hour and a half, 90 minutes.
Okay.
Okay.
Nice.
It's on the front of the paper. When you look at the exam paper, see if I've got a front page to hand here. I've got piles and piles of notes. Do you bear with me for a second? Where are we? If I just try and find the front page. You have to bear with me for a few seconds while I do that. On the front page, I'll switch to the desk camera. On the front page, it tells you it's 1.5 hours. So on the front page of all the UFP papers, it tells you exactly how long you've got to do it. Okay?
Okay, sir.
Right. Any other questions?
No, thank you.
Okay, so your work to finish off this lesson, which you've got about another 20 minutes or so to go, your work to finish off this lesson is obviously to make sure you've gone through the past paper that I've just walked you through, and then make sure you do some revision beyond that, ready for tomorrow, when I'm going to ask you to do that as a mock. You've got a few days to do it. Obviously, in the real exam, you have to download, print out, and do it on the day. But try to do this one within the first couple of days, so that I can then go through it next week.
Yes, sir. I already printed I already printed. Just a bit.
You already printed. Great stuff.
Yeah.
Okay, Albert, anything else you need?
No, thank you, sir. I hope you
Okay.
are safe.
I'll see you. Oh, I'll
Tomorrow should be.
well, tomorrow you're doing the paper, so
Oh
it'll be
yeah.
next week. Okay.
Mm-hmm.
Okay. All right. Take care, mate. Bye.